We are going to find the eigenvalues and the eigenvectors for this 2x2 matrix. We call this solving the eigenproblem for the matrix. So we're going to solve the eigenproblem for this matrix. The eigenvalues first. So let's take a look at the eigenvalues. The equation there is that the determinant of A, this matrix A, minus the eigenvalue lambda times the identity matrix should equal 0. So we just need a determinant here that this is the determinant of A minus lambda I. I only has entries on the diagonal, so the lambda only shows up on the diagonal. So this looks like 3 minus lambda, negative 1, 4, and negative 2 minus lambda. That is what A minus lambda I looks like. We want the determinant of that. We get the determinant by multiplying these elements on the diagonal. That's 3 minus lambda times negative 2 minus lambda minus 1 times, or negative 1 times 4. So that equals lambda squared minus lambda minus 2. And that should equal 0, right? The determinant should equal 0. So we want lambda squared minus lambda minus 2 to equal 0. This factors, this is lambda minus 2 times lambda plus 1. And so we have lambda equals 2 and lambda equals minus 1. There are two eigenvalues for this matrix, and they are 2 and negative 1. We're now going to take each one at a time and see how to get the corresponding eigenvector for it. All right, so now that we have the eigenvalues, 2 and negative 1, let's find the corresponding eigenvectors. First, we'll take lambda equals 2. That's our first eigenvalue. We want to find the eigenvector that goes along with this. The eigenvector equation is similar to the eigenvalue equation, but it's a vector equation. There's no determinant, so it's vectors instead of scalars. And it looks like this. So what does that look like for us? It looks like A minus 2i. So that's 3 minus 2, negative 1, 4, and negative 2 minus 2. So again, subtracting that eigenvalue in the diagonals. And then V is a V1, V2 vector. And of course, 0 is just a 0, 0 vector. So here's our system of equations. This looks like 1 minus 1, 4 minus 4 times V1, V2 equals 0, 0. So this is two equations for two unknowns. If I do the matrix multiplication now, multiply this matrix times this vector, the equation I get is V1 minus V2 equals 0. And the next equation I get is 4v1 minus 4v2 equals 0. So I always have two equations at this point, and they're always redundant. These two equations, if I divide the second equation through by 4, I get the first equation. So these are redundant, which is normal and expected and usual and always happens in these eigenvector, eigenvalue problems. So we really just have the one equation, so we'll take it. We have v1 equals v2. From this first equation, and I can now just pick a value. I'm going to pick v2 equals 1. That means v1 also equals 1. So my eigenvector is 1, 1. It's the vector 1, 1. I have v2 and v1 are both equal to 1. This could be 2, 2, or negative 1/5, negative 1/5, or 100, 100. As long as v2 and v1 are the same, we satisfy this equation. So there are actually infinitely many correct answers for the eigenvector, and they're all multiples of each other. So we just want to pick whatever the simplest one is. In this case, it's 1, 1. We can pick any multiple of that. We could have picked 2, 2, or 3, 3. We cannot pick 0, 0. We can't have a 0 eigenvector, but any other multiple of this would work, and we want to pick one that has integers and that's relatively simple. So this will do for us. If I pick 2, 2 here, I still get the right answer when it comes to differential equations later on. But we'll try to keep it as simple as we can when we have these options. So that's our first eigenvector. Let's go ahead and clear the screen and then do the second eigenvector. All right, we're ready to do the second eigenvector. We found the eigenvector that corresponds to lambda equals 2. Now let's find the eigenvector that corresponds to lambda equals negative 1. In this case, our A minus lambda I times V equals 0 equation is 3 minus a negative 1 is 4, negative 1, 4, and then 2 minus a negative 1 is negative 1. V1, V2 equals 0, 0. All right, so we have 4v1 minus v2 equals 0. And the second equation is again redundant. It's the same as the first equation, so we just need the one. And that is 4v1 equals v2. So let's pick v1 equals 1. If v1 equals 1, that's v1 is the top element of this vector. And if v1 is 1, that means v2 has to be 4. So there's the eigenvector for this other eigenvalue. In the end, our matrix has a lambda equals 2 with an eigenvector of 1, 1, and a lambda equals -1 with an eigenvector of 1, 4. And that is the full solution of our eigenproblem, our two eigenvalues and the corresponding eigenvectors.